Okay, I've got a three-part series that's going to introduce you to ANOVA, single factor ANOVA. This first one is going to introduce you to ANOVA and the terminology that we use in ANOVA. ANOVA stands for Analysis of Variance. Let's look at an example here that we're going to use in the next couple of screencasts. We have burritos here, and this is the mass of burritos at 4 different restaurants. We've collected 5 different replicates, so you notice that in each restaurant you don't have exactly the same mass. We have some sort of variation within a group. Sometimes these are known as treatments or groups, these different restaurants. And if we plot these in a box plot, you notice that there's differences between these 4 groups. We can look at, in these 4 groups, the grand average. This is the overall average. If you were to average the mass of all of these 20 burritos, you get a grand average of 596. This brings up a new notation, a new terminology here. We have y dot dot bar. I'll talk about this in the next slide, but that's known as the grand average. The various groups or treatments, illegal Pete's, Q1, Q2, and Chipotle, all vary a little bit from the grand average. We can also look at this graphically as kind of a column chart where each of these bars represents a single burrito mass. And you see that we have groupings of 5, and there's variability. There's variability within groups. That means within each of these restaurants, but there's also variability between these different groups. And ANOVA sort of looks at error within groups and between groups and comes up with a conclusion. So some terminology in ANOVA. We have A, lowercase a, this is the number of treatment levels or groups. In our burrito example, this would be 4. We have 4 treatments or groups, restaurants in other words. N is the number of samples. These are the number of observations per group. It simplifies things tremendously if the sample numbers are the same, but you can also adapt ANOVA in case you've got unequal sample sizes. But in this analysis, we're going to assume that we have that N is constant. Capital N is the total number of samples or observations, and this is equal to the number of treatment levels multiplied by the number of samples. And we've got this notation y dot dot. Y dot dot is the sum of all yij. I represents the index for the different treatments, and j represents the index for the number of samples. So if we sum over all observations, we get y dot dot. That's the sum of everything. That's the sum of all our observations. Y dot dot bar is known as the grand average of all our observations. And in its simplest form, that's just y dot dot divided by big N, the total number of samples. We can also determine y1 dot. So that's when I equals 1. This would be for the first treatment group. And y1 dot is just the sum of all yij, but only in that first treatment group. For example, this would represent the sum of all of the masses in the illegal Pete's group. We could also compute y1 dot bar, which would just be y1 dot divided by little n. Graphically, y dot dot bar is just that grand average that we talked about earlier. That's just mu in my previous diagram. In ANOVA, it's important for us to calculate total sum of squared. This is really similar to what we've done already with regression. The terminology is a little bit different, but in essence, we're taking the difference between all of our data points from the grand average, and we're squaring those. So our residuals, Eij, is just Yij minus the grand average. So if we looked at this graphically, we would have residuals in group 1, group 2, group 3, and group 4. You see these residuals are either negative or positive in general, depending upon the different treatment groups. If you were to sum all of these residuals, by the way, they would approximately equal 0. So let's take a look at one-way ANOVA. Just some additional terminology. This is known as single factor, what we're talking about today. One way is synonymous with single factor ANOVA. We have a single factor, and that is the restaurant. That's the only thing that we are varying. There are 4 treatments or levels of factors. We have 4 different restaurants, so A is equal to 4, and we take 5 observations at each level, so N equals 5. Our objective with ANOVA is similar to the ANOVA that we use for regression analysis, and that is we want to determine whether the factor with its given treatments has any effect on the response. Okay, so all we're trying to do is to determine in this case, does choice of restaurant affect the mass or the output? And that's really all we're determining with one-way ANOVA. The general form for the data when we do this in Excel is we have our observations in different rows and we have our different treatments in columns. We then sum or total each column to get y1 dot, y2 dot, etc. We calculate the averages, y1 dot bar. y1 dot bar is just y1 dot divided by little n. And we can do this for all of our treatments, our different groups. We can also compute the grand total, y dot dot, and the grand average, y dot dot bar. The grand average is just the grand total divided by capital N. ANOVA applies to a completely randomized design. So in other words, when we collect the data, we've randomized the experiment. The treatment levels have also already been chosen, and this is usually referred to as a fixed effects model. We've already chosen the treatment levels before conducting the experiment. And just FYI, in this case, we have assumed the same number of trials at each treatment level. It does get more complicated, but it's doable if you have different trials at each treatment level. There are two types of models, and they're equivalent. The first one is what we refer to as a means model. Each observation that we see of our 20 observations in our example can be given by a treatment mean, that's what mu I is, plus some sort of random error. So Yij is our observation, mu I is the mean of the ith factor level, and again we have random error. There's also an effects model which mathematically is identical, it just looks a little different. Each of our observations can be given by an overall mean, so that's the grand average of all of our data, plus some sort of treatment effect, so this would be the ith treatment effect, and we denote that by tau, and again we have our random error. Let's take a look at the means model. Here we're zooming in on our burritos and we're just looking at the first treatment. This is illegal Pete's. Every observation we see when I equals 1 can be given by the overall mean of group 1, so that's mu1, plus some sort of epsilon or variation from that mean. In the effects model, instead of coming up with a treatment mean, mu I, we replace treatment mean with mu, which is our overall mean, our grand average, plus a treatment effect, tau I. And so we can replace mu1 with the grand average mu plus some sort of treatment effect, tau 1. Mu up here is the grand average. That's the same as y dot dot bar. So each treatment, each group, has a different tau I, or tau. In this case, tau is going to be negative because burrito mass of illegal Pete's is generally a little bit less than the overall average. It turns out that this effects model is the typical one to analyze when talking about ANOVA, and so that's what we'll be using in our subsequent analysis. In ANOVA, we set up a hypothesis test. The null hypothesis is essentially all of the means for the different groups. Mu1 equals mu2 equals dot 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 equals mu A for all of our treatment levels are equal. That's our null hypothesis. And if we can just prove that there's at least one pair whose means are not the same, then we can accept the alternate hypothesis. And if we accept the alternate hypothesis, then we just claim that the treatment, or the restaurant in our example, affects burrito mass. And that's really all we can conclude. Alternatively, and actually this is more common, our null hypothesis is the treatment effects, tau 1 up to tau A, are all equal to 0, so there's no treatment effects. There's no differences between the restaurants. And our alternate is that for at least one I, there is a treatment effect. And so this is an alternative way that we can set up the hypothesis to be tested using ANOVA. In the next screencast, I'll show you how we can partition the sum of squares and we can perform this hypothesis test in Excel.